Hello people, so this is going to be a video about the SHA-1 versus SHA-2 signature algorithms for SSL certificates. So in the last video we went over the actual SSL certificate trust chain. So we looked at basically how each certificate in the chain links to the parent and all the way up to the trusted root. So please have a look at that video if you haven't already and you don't understand what an SSL certificate chain is. This one is going to be focusing on a very important and topical part of it right now, which is the actual signature algorithm that's being used to sign the certificates. And we're going to take you through a sort of a workflow of how certificates are signed, and then also how they're validated by the browser when somebody goes to a website using that certificate. Once again, this stuff can be a little bit involved. It's not going to be a short video. There are lots of short videos on YouTube about SSL. When I wanted to learn about them, none of them really actually explained it in a way that was very accessible or in a level of depth that was satisfying for me. So hopefully if you've seen some of the videos in the series so far, you will sort of see what kind of level I'm pitching at, and if I repeat myself, again, I'm sorry, but I think the most important thing is that the concepts get explained, and hopefully it won't take too long. So basically, SHA-1 is as explained in a previous video about signature algorithms, is a hashing algorithm that basically enables you to sign a document and create a unique digest to represent a certificate. SHA-2 is a family of algorithms which are more secure than SHA-1, and in particular what that means is that the message digest that gets created is a longer string. It's a longer string of characters, which means it's actually much more difficult to find another input that will basically create that same string. And we'll see how that actually applies to the world of SSL certificates, and how that vulnerability, the possibility of creating that collision in the hash algorithm, enables potential wrongdoers to basically exploit the system and ultimately masquerade as different websites. I'll be explaining exactly what the vulnerabilities are. I think again there's a big kind of misconception about exactly what the vulnerability is. For example, if I'm HSBC website and a client connects to me and I'm using SHA-1 versus SHA-2, does that actually mean that there's a risk that that an interceptor in the middle will be able to actually listen in on the traffic going back and forth? Well, actually, no, that's not what's at stake here. This is actually more, the vulnerability here is about the ease of another person setting up a website pretending to be yours, and then putting themselves potentially in the middle of your website and the client, and then perhaps they can do things like intercept the traffic that's coming from the client and then sending it onto the server and sort of using their fake website as a kind of intermediary. I mean, the end result could be the same, but it's really important to kind of understand who the different players are in terms of, the client wants their data protected, the server, as in HSBC or whatever, they want their data to be protected, and then obviously the wrongdoer in the middle, his interest or hers is to actually to be able to listen in on traffic and do all sorts of dirty, horrible things. So I'm going to do another screencast, and basically, hopefully, things will become clear. Some of the diagrams look a little bit scary to begin with. Sorry, this is not extremely simple, but hopefully, because I'm going to explain it in a way that's quite deep, the diagrams will eventually not be so intimidating. Okay, so just starting with a recap of basically the last session. So here we have the slide that we went through. We have a trust chain here of certificates, and starting with the end user certificate here. I'm just going to graffiti this diagram. So this is the end user certificate, We have the relationship between the issuer and the subject of the parent certificate. Again, if this is, I'm not going to go over this in detail again. Please see the previous video. But that was all about how this trust chain works, what the various stages of the hashing and encryption and signatures actually mean. And these were actually real certificates. And in this case, we use the HSBC certificate that you can see in your browser. So rather than use actual certificates which have a lot of kind of noise on them, I'm going to basically use a sort of simplified version for this tutorial, but the concepts are the same. Apologies that in the next diagram the order in terms of left to right has been reversed. That shouldn't be too much to get your head around, but just to avoid any confusion. Okay, so let's go into the next, or the first slide of this presentation. So here we have the first slide, and it's a very simple trust chain. As I said, it goes the different direction to the previous slide. So we have the bank's server-side certificate over here. These green lines, please don't get too distracted by these. I'm going to sort of pencil over these. They're just to set the flow. So if you try and sort of look at this diagram, ignoring the pale green lines, they will become more clear. So we've got a trust chain where we have the bank, which is HSBC. They have a server-side certificate. We have an intermediate certificate, which is basically an intermediate certificate authority has signed the bank's end user certificate, and then that intermediate certificate is signed by the root certificate, right? And so it's a three certificate trust chain. Now, what I want to do to start with is basically the first part of this is taking you through the actual process of signing the certificate. Okay, so if we start at the root certificate and say, right, before these two even existed, the root certificate has to exist, because the root certificate signs the intermediate certificate, and the intermediate certificate signs the end server certificate. So this root certificate here could be a VeriSign or whoever the case may be. What happens here is that the signature of the root certificate is generated as follows, and I think this should be familiar with from the previous video. You basically take your entire contents of the certificate, all this stuff, including the public key of the root certificate. They would pass it through a hash function, and which hash function you use, so SHA-1 or SHA-256, depends on what has been specified in the server certificate. And this video is actually all about the implications of choosing SHA-1 or SHA-2 or SHA-256. SHA-256 is one of the SHA-2 family. So there are various algorithms within the SHA-2 family. The most commonly used one is SHA-256, and SHA-256 is characterized by a 256-bit hash string. Okay, so to generate the signature, the root certificate will be hashed. Okay, and the results will be passed into an RSA encryption algorithm, along with the private key of the root certificate holder, right? The root certificate authority. So this public key and this private key, as always in RSA, as we've been through in previous videos, they very strongly match together. They can't work one without the other. So the private key is used to encrypt the hash of the root certificate, and the result, hey presto, is going to be the signature of the root certificate, and that's fine. And as we discussed in the last video, this root certificate is a self-signed certificate, i.e. the signature is generated, it's signed with its own private key, which means that in order for it to be trusted, it has to be kind of hard-coded and implicitly trusted by common browsers and any other end-user applications. There's nobody else to go to look for for authority. So each time, so all these browsers like Internet Explorer, Chrome, all these applications, they have their own key stores, and they depend on certain reputable companies like VeriSign, etc., to basically update them with their root certificates. Okay, so we have a root certificate. Now, how do we actually go from there to generate an intermediate certificate? One of the things we're going to talk about as well is why we need intermediate certificates as well, because that's not immediately obvious at first. When we actually talk about how these certificates can actually be compromised, we'll actually explain the need for intermediate certificates and why they're there. Okay, so to generate an intermediate certificate, what happens is the intermediate certificate authority will go through the process explained in the previous video to obtain this certificate. They will set up they will decide the signature algorithm. So again, is this signature going to be using a SHA-1 or a SHA-2 algorithm? Then they will also decide who the issuer is going to be. So who's going to sign this intermediate certificate. So in this diagram, obviously it's the root certificate here that's going to be signing it. So this issuer here corresponds, and that's what this green line is for, to the subject of the root certificate, right? And that chain is explained in depth in the previous video, right? So that's that relationship there. Now what happens here, so the intermediate certificate, as all certificates do, has a corresponding public key and private key, right? Private key is always kept private to the intermediate certificate authority. The public key forms part of the certificate. I know I'm going over and over this, but now same thing happens again. So the entire certificate is hashed according to the signature algorithm. So is it SHA-1, is it SHA-2? And the output of that hash, once again, it goes through the RSA encryption algorithm. And the key point here is that the private key that we use to encrypt that hash and generate the signature is the private key of the root certificate, right? The parent certificate. And that relationship is defined by this line here. So once we've generated the signature out of there, let's draw a curved line there, then we have a signature, right? We have a signature for the intermediate certificate authority, right? Now, when HSBC come to get their own certificate, they will have their certificate, their end user certificate, signed typically by an intermediate trusted certificate, much like this one. So again, the same process happens, but one step further down the tree. So HSBC themselves they will basically apply for a certificate to be signed by this trusted intermediate certificate, and they will decide what the hashing algorithm they want to use to sign it. So are they going to go for SHA-1 or SHA-256? Their issuer, they say, okay, well, we want our certificate to be signed by intermediate CA. So we like those guys. We're going to get them to sign this. So that relationship applies there. And then once again, this entire certificate is going to be hashed. It's going to be hashed according to the signature algorithm here. It's going to go through the RSA encryption algorithm, and once again, it's going to be encrypted using the private key of the parent certificate. Right? Hopefully, this is all a little bit clearer by now, and that becomes the signature for the end user certificate, for the HSBC certificate. So at that point, HSBC has a complete SSL certificate with a public key, its own private key, which it keeps totally private on the HSBC web server, and now it has a certificate that it can send to all the clients who want to communicate securely for online banking, etc., etc. So the browsers will request https hsbc.com and log in, and HSBC will send, in the response, they will send their certificate, not the private key, they will send this. They will also send the intermediate certificate in the same response. So they'll send all of this, these two. They will send that back to the client, and the client will basically undergo a validation, right? And I'm going to show the validation process in the next slide, sort of down here. If you think of it like everything on the top here is about the actual the creation and the signing of the certificates, and then I'm going to illustrate the validation on the bottom here. Now, and the key thing is, as I mentioned before, the validation will happen rather than top to bottom, it'll happen bottom to top. So the browser will first validate this one, it will look at the issuer and say, do I have a certificate corresponding to that issuer? It will, and because we sent this one in the response, it will find this one and it will say, okay, that looks good. Let's see if we have a valid certificate for the issuer of this intermediate certificate. And in this case, we didn't send the root certificate. We didn't send that in the actual. Sorry about the horn. We didn't send that in the response. But as I mentioned, this root certificate here is actually embedded and trusted inside the browser of the client. So at that point, the validation is successful. The browser basically says, well, listen, if this certificate chain ends at this trusted root certificate here, then that's good for me. I trust, therefore, anything down further down in this trust chain. So we've covered the actual signing of the certificates, how they're actually generated. So now, if we talk about what happens when the certificates actually are validated by the users, so when those certificates are installed on the HSP website and clients, browsers can actually come in, log in, and start actually interacting with our website, right? So let's assume, since we're talking about SHA-1, that our certificate chain is using SHA-1 certificates across the board. But let's follow the bottom half and see what's going on here in terms of the validation of the certificates. So client connects to HSBC website, right? HTTPS www.hsbc.com/login. HSBC, as I mentioned, is going to send a bundle of certificates in the response. Basically, it's going to send the end user certificate, and it's going to send the intermediate certificate back in the same response. It's not going to send the root certificate, right? The root certificate is actually in the trusted key store. It's already on the client system. You and I and everybody else has it already in their browser. But these two are sent back in response to the client when they establish the connection. Okay, so what happens down here is very similar, but kind of in the reverse process of what happened in terms of the certificates being generated and signed. So let's just go through it. It's step by step. It's a bit detailed again. I'm going to kind of try and trace over these green lines and make some sense of them. I've kept the green lines from the signing part just to show the full picture, but probably it could have been a bit clearer without them. Anyway, so if a client wants to basically validate that this public key that they received actually belongs to HSBC, so that they are genuinely connecting to the people who claim to be HSBC. They are genuinely connecting to HSBC. I'm just going to write intermediate just in here, CA. Apologies for my terrible handwriting. Intermediate. I'm just going to abbreviate it, and then I'm going to call this VeriSign root, and then I'm going to call this one, well, this one is self-signing, so this is basically the same, the subject and the issuer are the same, and then the intermediate certificate is of course signed by VeriSign root. Right, so we've seen that relationship in the previous slide already. So what happens? The browser has to validate this entire chain. The first thing it does is all about basically checking the signatures, making sure that nothing inside here, in particular the public key, has been changed. We went over the dangers of this in previous videos, that's all about the man-in-the-middle attack, basically. So basically, we want to make sure that that this signature was indeed used to sign this certificate, right? So first of all, again, we take this entire certificate contents, right? And we're gonna, because we're using SHA-1 across the board here, so we're gonna basically we're gonna take all the contents, and I'm just gonna trace over here, and we're gonna put it through this SHA-1 hash function, right? That's the first part. Then what we do is we take the signature that we're trying to validate, right? And we say, okay, well, who's the issuer of this certificate? Okay, well, it's intermediate CA. Do we have a certificate to hand, so either in the response or in the trusted key store, which corresponds to intermediate CA? In this case, we got one from the client, sorry, from the server. So yes, we do have one. Fantastic. Okay, well, we know that intermediate CA were the people who signed this certificate. So what we do is we say, right, well, take this signature, and we're going to decrypt it using the public key of the issuing certificate, right? And then we put that through the RSA decryption. And then we have two things that should be the same, right? Because if you follow the previous slide and see how the signature was generated, and you've seen the previous videos on the whole kind of public-private key encryption, you should see how that works. If you don't, then ask me a question, I'll explain it. So if these two are not the same, then you've fallen at the first hurdle, right? Clearly something has happened. The contents of this certificate have been changed since they were signed, since the time they were signed by intermediate CA. At that point, the browser is going to say, sorry, this does not check out. Be careful, because you might not be connecting to HSBC, you might be connecting to somebody else. So in that case, you will be invited to abort the session or carry on at your own risk. Now, assuming that if it does check out, so down the yes branch here, if this does check out, then, oh, I wish I could draw in a straight line, then we turn our attention to the issuer. We have to basically step one up the chain and validate the next intermediate certificate. So we've already established this certificate is signed by intermediate certificate authority. So we have that in our response. We already have it to hand. The client has it ready to process. So we actually go and have a look at this intermediate certificate, right? So what do? Exactly the same thing. Take the entire certificate, my apologies, and we are going to put that through the SHA-1 hash function, right? SHA-1 again, because we're using SHA-1 to sign all these certificates. And then we have the output of that. Once again, this intermediate certificate was signed by the VeriSign root certificate. That's all. That's basically defined in the issuer here. So again, we have to say, right, well, we know if this signature was generated and signed by the VeriSign root private key, then the way we validate it is we say, take the signature, and then we use the public key belonging to VeriSign root, and we decrypt that using the RSA decryption algorithm, and again we have two things that should tie out. They should be exactly the same. If they're not, then again we have a problem. The problem this time is that something in the intermediate certificate doesn't add up. So the end user certificate was fine. The signature, the hash of the signature, or the hash of the certificate matched the signature, but this could have been a man-in-the-middle attack. This could be somebody could have modified the public key in this certificate. So you'll get the same browser warning, and you'll be invited to abort or continue at your own risk. If they do add up, if they do check out, if they're exactly the same, then the last piece in the jigsaw is basically making sure that it's basically stepping one up the chain to the issuer of the intermediate certificate. In this case, we've already established it is the parent certificate is VeriSign root, whatever the case may be. So again, we ask, well, do we have the VeriSign root certificate available? Now, it didn't come in the response from the bank. That's the whole point. we don't rely on the end user, the server, to send us the root certificate. The whole point is that the server, or whoever's pretending to be the server, could actually just could be masquerading as somebody else. So what we have is we have these trusted certificates in our key store, one of which is VeriSign root CA, right? And we say, okay, well, we have this certificate in our key store, so let's basically, at that point, we're fine. We can do the validation, so we can say, well, let's look at the signature of the VeriSign root certificate that we have installed already on our local key store or cached in our browser, and the exactly the same principle should apply. So if we take the this entire certificate and we pass it through the SHA-1 hash function, it should be exactly the same as the decrypted signature using the public key of the same certificate. So if you look at the diagram here, this decryption of the server certificate was done using the parent's public key, and this validation of the intermediate certificate was done using the parent's public key. But because the root certificate is self-signed, it means that it signed its own certificate using its own private key. So basically, to validate the signature, you just basically use the same public key within the certificate. This validation is actually not really part of the proceedings on the client side, because this certificate in its entirety is already installed and distributed and embedded within all client browsers all around the world, yours, mine, everything. So there's really very little scope for something to go wrong, for the contents of this to be kind of modified, right? So that's basically the process of so the top here. That's an extremely horrendous diagram now, but the top part was all about the actual signing of the certificates, and the bottom half was the process in reverse where we're validating them. So what I'm going to do now is basically go on to the next slide. I'm going to talk about so why SHA-1 and why SHA-256, or why not SHA-1. What's the motivation behind the industry migrating to a SHA-2 standard, and what kind of vulnerabilities does that mitigate against? So let's keep going and let's go on to the next slide. So we're back on the old sort of three certificate chain diagram again, copied from the previous slide, and I'm just going to show you what can happen in basically some of the common scenarios that might represent a compromise. The most basic one would be if this bandit over here, if they got control, if they got access to the private key of one of these intermediate certificate authorities, then what they could actually do is say, well, actually, I'm just going to create my own spoof website. Let's say I'm going to call it hsbcbank.com, and hsbc.com is the proper HSBC website, but hsbcbank.com is my spoof website that I'm going to pretend to be HSBC, and I'm going to use the private key belonging to the known semantic intermediate certificate authority to basically take my certificate with my own public key and my own private key. Well, the private key is obviously not in the certificate, but my public key is. So take the private key and basically use it to sign my own certificate, and then I can actually install a website and install the certificate on that website, hsbcbank.com, and there you go. I mean, I can put it up there. If somebody comes across hsbcbank.com, they might believe it's HSBC. Their browser will tell them that they have a trusted chain all the way up to here and all the way up to the VeriSign root CA. So the point is that whole trust chain is being compromised because we've actually got access to the private key of the intermediate certificate authority. And this actually also illustrates, I did mention I was going to talk about this, why we need intermediate CA. Why do we need intermediate certificate authorities? Because if we just had a scenario where all of these, so basically all our end user certificates, like HSBC, the ones that are installed on the websites, if they were all signed by basically this one root certificate authority over here, and somehow somebody got access to the public key, or this certificate was somehow compromised, every single certificate that's been signed by this one would have to be thrown out, right? Whereas if you think about if this one in the middle is being compromised, then it's only the ones downstream from here that need to be basically thrown out, that won't be trusted. All the ones that, so if we just draw a little tree over here, so if the root of the tree is basically our this VeriSign root CA over here, this is our root, and then that root can basically sign a number of intermediate certificates, right? And it can go down several levels, and then each of these can then sign, you know, a whole load of SSL certificates for end user websites. This might be another intermediate CA, and then that might sign 3 other intermediate websites. So these ones here are all just websites, and this one, and then the ones sort of that are not leaf nodes in the tree, these are intermediate certificate authorities. Now, if somehow this one gets compromised, like that somebody steals the private key, or somebody manages to find a hash collision for the certificate, well, I'll talk about that in the next one, then it's only these ones that are affected. And what will happen when this certificate is actually corrupted is that a notification will be sent out, and eventually browsers around the world will get an update saying basically that this intermediate certificate is actually on a revocation list, and basically, so if unfortunately for these poor people down here, their websites, they will need to get new SSL certificates, because when the browser, right, so let's say this browser here, you know, in Internet Explorer is going to this website here, right? Now this website is going to send obviously its own certificate, and it's also going to send the intermediate certificates in the chain all the way up to the root. It's going to send that to the client, right? And the client basically checks all those certificates in the chain, and when it checks this one, it's going to see, okay, that's in the revocation list, as in it's a widely known compromised certificate, and therefore the browser will not trust this website, right? So anyway, that's basically a little bit about, that's one compromise scenario. That's very rare, because these certificate authorities, they take extreme precautions to make sure that their private keys are not compromised. Apparently it's like Fort Knox if you go and actually visit one of these places like VeriSign or Semantic. So the next one is going to be about another type of compromise, and that type of compromise is basically, this is more to do with the SHA-1, SHA-2 thing, which is actually the point of this video. Now, so basically, so we have our, I've ignored the root certificate here, I've ignored it, right? But so we've just taken the second and third certificates in the chain. So we've got our HSBC certificate over here. It's signed by the Semantic Intermediate Certificate Authority. So that relationship is there as always. And so what we're looking at, we've seen this before, again earlier in the video. If we take the hash of this certificate, right, and then compare it with the signature, which when decrypted using the public key of the issuing certificate, so basically traversing this relationship here, taking the public key and using that to basically decrypt the signature, these two things should match. If they do, then this certificate is considered validated, and then we go on to validate the intermediate certificate. Anyway, so key question: if this bandit over here can find a way to generate his own certificate for hsbcfakebank.com or whatever, and if he can play around with the contents of the certificate using some strange hidden characters, etc., and if he has enough computer power to basically try lots of different combinations. If he can actually tweak it so that basically when he hashes this certificate using a SHA-1 or SHA-256 algorithm, depending on what the, let's say this one is using a SHA-1 hash, right? So if the bandit basically plays around with his own fake certificate, which he's free to generate on his own computer, and he plays around and puts it through a SHA-1 hash, as soon as he finds one where the hash is equal to this one, these are only the first 4 characters, but you know the SHA-1 hash would be 40 characters long. If he can do that, then he can basically say, right, well, what I'm going to do is I'm going to reuse the signature, because I know this is a valid signature when signed by semantic intermediate CA. So I'm going to basically just copy that signature and use it in my own fake certificate, right? And then, because I've said, right, well, the issuer of my fake certificate is semantic intermediate CA, then obviously that propagates up to there, right? So then the bandit can basically install his, this is a bad diagram of a server, hsbcbank.com, my fake website. He's going to install this certificate on there, right? And then when some poor character on the internet basically does a Google search for HSBC or whatever, or finds finds a link to hsbcbank.com and connects, then hsbcbank.com, this certificate will be sent back to the client along with the intermediate certificate that signs it, and then the root certificate will be validated within the browser up here as usual, right? So the point is, because I've managed to create a collision, a SHA-1 hash collision, and find my own certificate that happens to have the same hash code as a known HSBC certificate, then basically I'm good to go. I can just reuse the signature and away I go. So that's the first type. Now I just want to show you also this can actually happen for finding a hash collision for an intermediate certificate as well. So I've reintroduced our 3 certificates back into the fold, right? So we've got our root certificate here, we've got our intermediate certificate here, and we've got our HSBC genuine certificate here. So now the bandit says, okay, well, what happens if, so I take this intermediate certificate, right, which belongs to semantic certificate authority. Now the hash code of that certificate is C4F8 blah blah blah. Again, let's say we're using SHA-1. Let's say we're using SHA-1 for all these examples because we're trying to show how vulnerable it is. So let's say that this bandit basically says, okay, I'm going to actually create my own fake intermediate certificate, right? And again, exactly the same. I'm going to keep passing it through hash function after hash function, keep playing around with a few hidden characters here and there, because each time I tweak any character, the hash is going to be completely different. And the hash we're looking for this time is C4F8. And if I manage to do it and find a certificate, right, like this one, where the hash equals C4F8, again, bingo, I can reuse the signature from the genuine intermediate certificate and just tag it on the bottom of my fake intermediate certificate. And then I'm in a very powerful position because I can then use my own fake intermediate certificate to sign all manner of fake websites. So I can create 100 fake websites. I can create a fake website for every single bank out there, every single online clothes retailer, whatever I want, just because I've managed to actually create a hash collision and a spoof version of an intermediate signing certificate. So in the next one, we've really kind of covered it. Now, so the question is, so why SHA-2 over SHA-1? I've just put a bit of text here because my handwriting really is terrible. And it really is down to this. I mean, what is the difference between SHA-2 and SHA-1? Well, so SHA-1 as we've written here, SHA-1 produces a 160-bit hash code, so 160 zeros and ones effectively, or 40 hex characters. So that hex character is basically 0 to 9 and A to F, right? SHA-256 produces a 256-bit hash value, and or equivalently, that is a 64 character 0 to 9 A to F if you want to represent it more in a more human readable way. So really, the scenario we've talked about above, it comes down to taking a real certificate like this, like a real known valid certificate, with a known hash value, let's say GA27F. If it's SHA-1, then there'll be another 35 characters, okay? And then designing a fake certificate, again, churning it through the hash function over and over again until you basically tweaked around and you found a combination that meets your needs. And that's an important point as well. It's extremely difficult to actually find any two documents that will give you the same hash at all, let alone one that is a valid SSL certificate with the exact details you want, and all that stuff. But the concern is that as computing power is on the up, the cost of computing power is coming down, that it's only a matter of time before people, that's organised crime, it's still a few years out yet, but before organised crime syndicates and all these kind of nasty organisations can actually create SHA-1 hash collisions on a fairly regular basis. And so SHA-2, it basically comes down to the fact that SHA-256 is so much incredibly more difficult to generate this collision for than SHA-1. So if this bingo situation here is basically it's just not going to happen, and that's why the industry is pushing all websites and to basically update their SSL certificates to a SHA-2 signature algorithm. The last slide is kind of like the boring part. So basically, what I'm just saying here is that so all the browsers like Internet Explorer and Chrome, they do have aggressive plans to kind of deprecate SHA-1 certificates, and I'm not going to go into the timelines. It's quite complicated. The different browsers have different sort of warning levels that they're gradually phasing in. One key one is that by 1st of Jan 2017, Microsoft will actually cease to trust all SHA-1 certificates, and that's no matter whether they're at the end level, like the HSBC, for example, or the intermediate certificates. So basically, what do you need to do? If you have any questions on this, as I said, ask below. But just to give a quick summary, you have to make sure that your website, for example, or your service, if it's not a website, will not basically work over HTTPS unless your client actually is SHA-2 compatible, which means that that client must be able to essentially perform a SHA-2 hash function. If they can't, then they won't be able to validate the SHA-2 signatures, right? Most modern browsers and stuff should be absolutely fine, but some older operating system and browser configurations and stuff can be a bit awkward there. And also purchase new SSL certificates signed by SHA-2. So you have to basically replace the SHA-1 certificates that you have on your website, replace them with SHA-2 certificates, and make sure that the trust chain, so the intermediate signing certificates along the way, should also be SHA-2 as well. And then the last thing is basically you need to make sure that your clients, so basically each client who's accessing your website, each customer or whatever, will need to have the root certificate of your new trust chain in their trusted key store, right? So for example, when you access a website on a Windows PC, so Windows has a sort of a key store of trusted root certificates, which are kind of, we've talked about it before, that's the list of certificates that it kind of implicitly trusts. And basically, so when you actually trust a new certificate in your browser, it actually gets cached, or it gets installed in your actual Windows trusted key store. I won't go into too much detail there, but if, for example, your client is perhaps not a web client, but it's let's say there's a like an application client that's connecting to your system, and that application is running on an enterprise Linux box somewhere. Then you would need to make sure that the actual Java installation on the Linux box has the new root certificate installed on their actual inside the Java key store. That's really it on SSL certificates. It's been quite a long journey. I think it started out as a kind of a introduction to sort of the very basic. I would say the three, if you think about it, the three main things we've talked about are the public and private key sort of asymmetric encryption, and also the I'm not getting any better at drawing, but the hash function there, which basically takes any input that can be represented as a digital asset and creates a sort of a unique code for that, and it's the combination of that with the keys that basically underpins all of the SSL chain, everything we've been talking about here. And the great thing is that these concepts are also, they underpin the whole Bitcoin and blockchain thing. And I think Bitcoin and blockchain is something that I've wanted to talk about for quite a long time. It's very interesting. I would encourage people to basically watch this series first before going on and watching that one, if you're not familiar with cryptography, because I'm not going to talk about the whole kind of Humpty Dumpty and all that kind of stuff all over again. But any questions on this or anything else, ask me below. If you do want me to make any more videos on anything related to SSL or anything else, also let me know. And thank you very much for watching, and let's see you in the next video.